Hi, welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me today,
Robert Moore.
So we are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. And so if you're watching live, happy Tuesday.
Happy Tuesday. What's so happy about a Tuesday?
We're alive.
Okay. That's a good thing.
That's enough. You don't need any more than that, right?
Yeah, you can ask for more, but
That's the bare minimum, right? You have to be alive to.
That's the minimum.
You have to be alive to appreciate anything, whether it's good health or otherwise.
Otherwise, right? So, I'll agree with you, but at the same time, and you people probably had a hard time hearing me because I didn't position my mic right. Anyway, it's a Tuesday.
And we're, more than halfway through the summer break.
We are. I don't know how I feel about that one. I don't know about you, but to a degree, it's like psyching myself up for classes.
So we have about 6 weeks to go, roughly
6 weeks
August
to go.
24th, and classes begin here on campus.
That's it.
Well,
So, yeah, people will be in the halls. People will be out in the lab making noise that we got to go out and hush them.
but it's always exciting to have new students come on campus.
It is. And don't get me wrong, folks. I love teaching. I love teaching new students. It just, it's on my feet for 2 hours.
Straight.
Yeah, it's like, okay.
What do you think about teaching the lab, I assume?
Yeah.
Yeah.
So they're 2 hours long, and you were pretty much standing and running the whole time. So,
Right.
because they always got questions about, hey, are we doing this right? I don't know. Are you?
Well, one of the things I like about starting of a new semester is, especially with my intro astronomy class, is usually I'll get, well over 100 students in each class. And it's a great opportunity to talk to them about new and exciting things in astronomy itself.
Kind of like what we do here.
It's kind of like what we do here. And the good thing about it is most of those students, as far as I can tell, really didn't pay a lot of it or haven't paid a lot of attention in the past to astronomical type of things that go on.
Right.
So they have sort of a cursory sort of, viewpoint of what's happening in the sky, which may or may not be correct.
Don't look up, right?
Right. Well, and it's a good time to kind of go over those kind of things and show people or talk about things for the first time that they kind of, get wow over and awed about and so on.
Yeah. It's one of the things I love about astronomy and love when you can roll out solar telescopes or big night telescopes, because you can wow people and you can show them, hey, look, stuff's real, it's not just pictures in a book.
Well, in some way, I wish the semester started today.
Oh, really?
Because there is a sunspot complex.
Oh, right.
Right? That's on the sun right now. So you can go to like spaceweather.com and other websites to get a real-time view of what the sun looks like. And you'll notice that one of the sunspots is extremely large. In fact, it's so large that yesterday I actually saw it on the sun using solar eclipse glasses. So don't look at the sun with just the eye unprotected.
Right. That's
Never,
that's
ever,
not
ever
smart.
do that. But if you use protection like looking through solar eclipse glass, especially made glasses that filter out most of the light from the sun, so allows you to look at it without damaging your eyes, you can see without magnification a dark spot on the surface of the sun.
Now, I'll go into and adding into that about the properly filtered. Welding glasses are not properly filtered. Those still allow through infrared light. And the infrared light from the sun is enough to boil the fluid inside your eye. So you will still damage your eye quite a bit by looking through improperly filtered lenses. And you won't see it because it's infrared. And we're not tuned to it. And hello, Mizuho. Nice to see you around.
Yeah, so what I have done in the past when we had an opportunity like this is I've actually taken my astronomy class outside on a nice day that's clear enough you can see the sun, and we just use solar eclipse glasses to look up at the sun.
Absolutely.
So real-time astronomy in that sense, right? So that's nice to do.
Yeah. Again, that's why I mentioned solar telescopes. I love solar telescopes for that reason, is because, otherwise astronomy is done, as I always tell students, in the cold and the dark.
Right.
But if you've got a solar telescope, you can do it in the bright sunlight, warm day.
Or if you're a neutrino astronomer,
Oh,
which is something hopefully we'll get to later today, later in this podcast, it doesn't matter when you observe,
right.
day or night.
Because neutrinos just go right through everything.
Yeah, so we'll talk about that a little bit later. But just to remind people, what Robert and I say on this podcast are just our own personal opinions. They're not necessarily the opinion of the university, College of Arts and Science, Department of Physics and Astrophysics, or anyone else related to allowing us to put this podcast together. And we also like to thank the university and the college and our department for allowing us to do this.
Right. I mean, it's great that they thought this was a good idea and allowing us to do it. So
exactly. So today we're going to start off by looking at some exciting news that's happened basically in the last 2 weeks. So last Tuesday, it was July the 4th, obviously a holiday, so the university was closed. We weren't able to do the podcast on that day. But there's been a lot of astronomy-related and physics-related news that's been kind of exciting that's come out in the last 2 weeks or so. So we won't be able to cover everything. There's not enough time.
right.
So I just picked out some nuggets, if you like, some juicy nuggets that I find personally interesting in myself, and hopefully others will also. So the first one we're going to start with then is results that come out from what's called NANOGrav. So you can see in this slide here, this is an image of the Green Bank telescope. This is the 100-meter telescope in West Virginia. This telescope has an interesting history. It was actually built as a replacement for a previous telescope that actually collapsed under its own weight.
Oh.
So the metal was fatigued. Nobody caught what was happening during the regular maintenance, and it just collapsed. Luckily, nobody was on the telescope doing any work to it at the time that it collapsed. This was a few years ago, and one of the senators from the state of West Virginia decided to come up with money, got it through Congress, to build a replacement telescope for the collapse of the older one. And this is the result, the 100-meter Green Bank telescope. This is the largest 100-meter fully steerable telescope in the world.
Right.
Which means you can point it at specific positions in the sky.
I want to mention, because people may not be aware of this, this is a radio telescope. This is essentially a big radio antenna that looks at radio wavelengths of light. So, this is not an optical with an eyepiece or anything like that.
So the beauty about looking at the radio wavelengths is that the clouds and the scattered light from the sun have no effect.
Right.
So unlike an optical telescope, if you're looking at something faint, you wouldn't look during the daytime, even if it was above the horizon, because the surface brightness, the brightness of the daytime sky would swamp the signal and make it extremely difficult, if not impossible, to see faint things.
Right.
But, you can do astronomy, optical astronomy in the daytime. I know people who actually go out, take their telescope pointed at Venus that may be visible only in the daytime, and you have to be careful, of course, not to point it at the sun. So if you're very careful in your position, you know what you're doing from a professional point of view,
Right.
You're not somebody who's new to astronomy. You can point it at bright objects in the sky, like brighter stars, like the brighter planets, and see them in the daytime sky if they're above the horizon. Right. Even though the sun is up, you still be able to see them because they're so bright.
I've recently seen pictures of Jupiter and Saturn in daytime sky, and you can tell it's daytime because it's this blue background.
Right. But looking at fainter things, for example, galaxies, the sky is going to be too bright because of the scattered photons from the sun to be able to actually see them, right, in most cases. But for radio astronomy, because it detects radio wavelengths, which are much longer than optical wavelengths, light coming from the sun, there are some radio photons, some radio, if you like, light particles that come from the sun. They just pass right through our atmosphere, unscattered essentially. And so therefore, if you had radio eyes and you were looking around in the daytime, the sky would look completely black. You might see the sun as a radio source, of course, or any other terrestrial radio sources that happen to be around on the ground. But essentially, the sky would be black, unless, of course, you were sensitive enough to see actual extragalactic radio sources, a long distance away. So in other words, you can do radio astronomy in the daytime, just so long as your target, and it may be some galaxy that you want to look at, long as that galaxy is above the horizon, then you can look at it even if it's completely cloud covered.
That's neat.
The only thing you have to watch out for, of course, if there are any electrical storms nearby.
Right.
Because the discharge of lightning will create lots of photons. Why? Because we can see lightning with our eyes. So clearly they must emit optical photons. but they also emit other forms of electromagnetic radiation, other wavelengths of photons, including radio. And you can test that yourself. How do you test that? Use an AM radio during a light, and you hear the occasional static, and that's the picking up of the radio photons from the lightning phenomena. And so lightning will create radio photons, and they can be detected by a nearby radio telescope. And that'll actually saturate or even destroy the detector, because usually we're looking at something very faint, but a lightning discharge would be an extremely bright source at radio wavelengths.
Lightning discharge is not faint in radio.
No, and so that would essentially damage the equipment. So as long as the radio storms are more than 50 miles away, you can do these type of observations. So radio astronomers can work day and night, which is interesting in that sense. You can get more out of your instrument in that sense, right?
You got more hours in the day.
Right. So this particular slide, while we're focusing on, and no pun intended when we're talking about telescope, we're focusing on the Green Bank radio telescope, is that this radio telescope, as well as a couple other ones like the VLA array in Socorro, New Mexico, and also the Arecibo telescope in Puerto Rico, which recently collapsed a couple of years ago, is no longer functioning. It's been destroyed. These three main instruments were involved in this project that's been going on for literally 15 years. And it's known as the North American Nanohertz Observatory for Gravitational Waves. That's shortened to NANOGrav, as you see here in the title. Now, way back in 2015, the LIGO instrument, the Laser Interferometer Gravitational Wave Observatory, first detected gravitational waves coming from a source. And this was the merging of two black holes. Now, this was one of these things, and we've had a separate podcast several months ago describing this in more detail about gravitational waves. I think it was one of our earlier podcasts.
I think it was,
if I'm not mistaken. And the gist of it, in case you didn't see that podcast, is that any type of masses that are accelerating, like objects that are asymmetric. So nothing that's shaped perfectly like a sphere with total homogeneous distribution of mass. We're talking about something that's sort of is asymmetric in the sense, imagine that you had one black hole that has a mass of 10 times the mass of the sun, and it's in orbit around another black hole, so they're orbiting around their center of mass, that has something that's different, like a mass of, 20 times the mass of the sun. Because we have a 10 and a 20 solar mass black hole, they're not the same. It's not like equal weights rotating around like a dumbbell type of shape, if you could think of that.
It'll wobble.
It'll wobble. And so this asymmetric distribution of mass produces, if you like, ripples or waves in the fabric of space and time, what we call space-time in general relativity. And so if you think of why is that? Well, there's technicalities you can go into. For those who know, it's quadrupole radiation, not dipole radiation, and so on, that gets emitted in gravitational waves. So that's why you need this asymmetric mass distribution. So any masses that are asymmetric like that, and it could be a sphere that you think is perfect, but it's not. It's a lump on the side, like an Earth object, right? Is not a perfect sphere. The Earth going around in its orbit around the sun, for example, obviously the sun has a lot more mass than the Earth. That would create or generate gravitational waves. A minute amount, but still gravitational waves. In fact, some, let's say a dumbbell-shaped object where one side of the dumbbell has twice the mass as the other side of the dumbbell, and you spin that actually will produce gravitational waves.
Not ones that we can detect.
Not at the present time.
Yet.
Yeah. You can never forecast, what's going to happen in the future like that, what will actually occur. So you never want to be caught, say, I will never do that. Because, chances are, maybe, hopefully not in your lifetime, you'll be, proven wrong type of thing, right?
I say never about a couple of things, but even I will admit, I hope I'm proven wrong. But
So the gravitational waves were first detected by LIGO instrument back in 2015. This is one of the predictions from the general theory of relativity that says these accelerating masses, then as we described, will create these ripples in space-time. And those ripples, decline in their amplitude, that is their strength, as they pass over greater and greater distances.
As waves tend to do.
Right. And so by analyzing the type of wave that we detect, we can estimate what is the origin or the progenitor, if you like, of those waves. And the way they do that is doing detailed simulation of different types of mass of black holes or other objects like neutron stars that are orbiting, spiral in with each other, and then merge ultimately. They produce a certain type of waveform, as we call it. Think of it as the shape of the wave. And we can match up those types of waves with what we actually observe to try to find out then what is our best case scenario in terms of constraining what was the origin or the source of these gravitational waves.
Right.
That's the nature of the beast, right? But more than just LIGO, there's other ways of detecting gravitational waves, and this is where the Green Bank telescope, and the other two radio telescopes come into play. So if we go to slide 2, this is the NANOGrav way of detecting gravitational waves. And so the big discovery that was announced near the end of June, on June the 28th of this year, was the first detection of gravitational waves by this technique. So this is not using the LIGO instruments. Now there are 3 of them that's running, LIGO and Virgo. And
forget the Italian one.
Yeah, no, so Virgo is the Italian one, and the Japanese one is
Japanese, that's right.
Kagra. Kagra is the Japanese instrument. And so all 3 of them started running in May of this year. So they're running now, as far as I know, with new upgrade of technology, and therefore more sensitive to weaker or different gravitational waves. Different, I mean, different frequencies or wavelengths, right?
Right.
So anyways, so it's mostly sensitivity that they're looking at, of course, in terms of upgrades here. But this is a different technique, right? So this is a technique is based on monitoring the signals coming from pulsars. Now, pulsars were first discovered in the 1960s. What they are is essentially neutron stars.
Right.
And so neutron stars result from the collapse of a massive star and the normal evolutionary processes that massive stars undergo. So massive stars collapse to the point where they have an iron core. That iron core cannot fuse into something heavier, so it's an endothermic reaction, as we say in chemistry,
it can't fuse and produce release energy,
rather than an exothermic reaction.
Right.
So ultimately, what happens in the process of the evolutionary state, the end state of a massive star, is that the iron core collapses in on itself. Densities go to, should I say it, astronomically high values. You're looking at densities of a neutron or nucleus, essentially, right? So nuclear densities and greater. The neutron stars, some of them, reportedly would have densities on the order of 100 times the nucleus of an atom. So we're extreme densities here. And what happens essentially is the iron atoms in these core at the end state of a massive star then get broken apart by the high energy gamma rays, photons that are produced. The temperatures go excess of 100 billion Kelvin.
Yikes.
These short wavelength gamma rays break apart the iron atoms. That's known as photodisintegration, breaking apart by light.
Right.
And what makes up iron atoms? Well, you have protons and neutrons and electrons, and under this high density environment, the protons and electrons squeeze together essentially to form neutrons, what we call in physics inverse beta decay.
Right.
Right. So normally if you take, for example, an isolated neutron, so if you took magic tweezers and plucked it out of the center of a helium atom and placed it somewhere all by itself and watched it for a period of time, what you would notice is it's unstable. It actually decays in roughly, on average, 15 minutes. Right. And what does it decay into? Well, it decays into a proton, an electron, and an anti-electron neutrino, which we're going to talk about a little bit later, as I mentioned. That's why I want to get the whole process. That's known as beta decay.
Right.
Okay. Beta was the old word that we used to mean electrons. So, for example, in radioactive decay, there's alpha particles, beta particles, and gamma rays. Well, alpha particles turn out to be helium nuclei once we did some experiments and analysis to understand it better. Beta particles turn out to be electrons, high-speed electrons on average. And then, of course, gamma rays are electromagnetic radiation, photons of light, a very short wavelength, of course.
They're from the nucleus cooling down.
Exactly. And so beta decay was the name given to this process. But in chemistry, if you think of a reaction occurring, under the right conditions, when a reaction goes one way, it could usually go the other way as well.
Right.
And so in this case, in that high density, high temperature, high pressure environments that we have inside of the core of a massive star at the end of its life, we have the inverse beta decay, where protons and electrons, if you want to think of it this way, get squeezed together to form neutrons.
Right.
So you build up neutrons, but there's already neutrons there from the disintegration of the iron atoms, the breaking apart by the gamma rays. So essentially you build up the fraction of neutrons in the center of these core, which was once an iron core. And these neutrons then collapse to the point, because of the high density and pressure, where essentially they put up a fight of getting closer to their nearest neighbor.
And now we're into a deep rabbit hole of uncertainty principle, exclusion principle, and yeah.
And this is known as neutron degeneracy pressure. And the way I like to think about it, a classical way, not to get into this rabbit hole as you suggest of quantum mechanics, but a classic way, if you want to just learn it a little bit for the first time, it's analogy, and all analogies break down, so beware of that. Is imagine you have a glass vase, okay, a glass container, and you want to say, how many marbles can I put in that glass container? Well, you fill up the glass container until it's full of marbles.
Right.
Right? And then you're like, well, I still have marbles left. You try to put another marble in. You might put it on the top. It falls over. Doesn't go in the vase. So you put it back again. Then you push on it with the palm of your hand. Okay? You try to squeeze in as many marbles as you can into your glass container. But you'll always get to this point where that last marble you try to put in, if you push on it with all your strength, and let's say you had enough strength to do that, you would break the glass container. It just will not handle or hold any additional marbles. Now think of those marbles as neutrons.
Right.
And so there's a limit of how many neutrons you can compact or put together in some finite volume of space, where essentially they resist being pushed even closer together. They're like, they put out their elbows and they say, that's it, I'm not getting any closer to any of the neutrons that are around me, the surrounding neighboring neutrons.
Right.
That's known as neutron degeneracy pressure, neutron pressure. So this neutron core in the center of these massive stars then, they resist further collapse. All of the material that's outside of that core doesn't know what's going on inside of the neutron core, so it rains in. And what happens is it runs into almost this brick wall type of analogy, and you have this core bounce where everything gets blown outwards. And what survives a lot of time are these neutron cores, which we call
neutron stars.
A neutron star.
That rebounding, by the way, is what we call a supernova.
That's right. And that produces a tremendous amount of energy gets released in the supernova, most of it in the form of neutrinos again. See how they show up everywhere?
Yeah.
Only like 1% of the energy that comes out of a supernova comes in the optical display, which is interesting. Yet that's the one that catches our attention historically the most.
Catches our eye.
That's, yeah, no pun intended, right? Again.
No, I fully intended that one.
So these neutron stars will form then as the end state of a massive star. Now, if you have a really massive star, what we discovered was even neutron pressure cannot prevent those neutrons from essentially squeezing inside each other, and the collapse continues. And what do you form?
Black hole.
A black hole, which we've gone into many times and we'll talk about later on today.
We'll probably talk about
well.
them many times on this show.
So these neutron stars, if you don't have enough mass to form a black hole, but you can form these neutron stars, some of their characteristics would include that they would spin rapidly.
Right. Conservation of angular momentum.
That's from the conservation of angular momentum. So think of a figure skater, and they're doing a spin, and they got their arms outstretched. And if they want to speed up their rotation, they just draw their arms toward them. So you decrease the physical extent of the object, and that'll cause you to spin up. So your rotation period then would decrease. It takes less time to go around once. So because you have initially a massive, large star to start with, and as far as we know, and I don't know any exceptions to this unless it's, these very special cases or it's been artificially done, almost everything has some amount of rotation.
Right.
The rotation could be a little bit, and sometimes it's a lot, but there's a little bit of rotation, which means everything has in physics what we call angular momentum. I mean, we're fixed to the surface of the Earth, but the Earth is rotating. That's how we have day and night. Right. So the Earth has a certain amount of angular momentum that you can calculate.
Yep. And it's actually fairly small compared to the size of the Earth. A lot of people don't realize that. They're like, oh, the Earth's spinning at 1,000 miles per hour. Sounds really nifty. But get on a merry-go-round that turns once in 24 hours. How thrilling of a ride is that?
Well, think of this. Imagine you're walking on the surface of some planet of some composition,
Right.
and it spins faster and faster and faster and faster. What would happen eventually?
You would fly off.
You would fly off, you see?
Right.
So there has to be a limit to the amount of angular momentum that an object would have that allows to walk on its surface in a 1G environment.
In fact, that's called breakup speed, if I remember correctly, right?
That's right. So if you want to have conditions conducive like we hear on the Earth walking around, right, there has to be a limit on how large the object is in terms of its radius, how much mass it contains, because we're looking for a 1G gravity field, and how fast it spins.
rotating.
And
Yeah.
we see that really show up when we look at what?
Oh,
Asteroids.
asteroids, yeah.
Right?
Because a lot of them we're finding are spinning at near their breakup speed.
In fact, you'd be very difficult for you to walk on a lot of those asteroids. They don't have enough mass, therefore not enough gravity. And if they're spinning, right, that adds into getting away from the surface, right?
Right.
If you think of, pseudo forces, right? The centrifugal type of forces, right?
Right.
So it'd be hard to be able to walk on the surface without having some kind of other technology, the
hold
way
you
that probes that shoot down with ropes attached to your arms that bury into the surface that hold you into the surface of that asteroid.
The bottom line, you could sneeze and launch yourself into space.
Well, that's
You
it,
could exceed
right?
great.
Assuming you had no
exceed
space
the
helmet
escape
on,
velocity.
right?
Assuming you had no space helmet on. Yeah.
You need particles to leave you.
Yeah.
The Newton's third law there.
I always found that interesting that they've got enough gravity to hold the little pebbles and everything together, but it's so small. That's about all it can do. You and a sneeze, off you go.
Well, I envision, astronauts in the future examining really low mass asteroids, but they're using jetpacks.
Mm-hmm.
I mean, I want to do that. I want to fly around in space with a jetpack.
Knock yourself out.
I'd love to do that. Imagine you could turn all different degrees of freedom and
Yeah.
direction.
It would be neat.
But that's what you need essentially, right?
Mm-hmm.
You need a way of sustaining. You do station keeping over one particular area of the asteroid.
Right.
To keep you there to do whatever type of thing you're trying to, whether it's collecting samples of it or whatever.
Right.
Anyways, so one of the predictions from the neutron stars as they're formed must that because the star initially is rotating, because of the conservation of angular momentum, they're going to rotate very fast.
Really fast.
And the other thing is really involves conserving magnetic fields.
Oh,
Now,
right.
most
yeah.
things have magnetic fields, including stars, like our own sun has a magnetic field. In fact, the sunspot we talked about that's visible now on the surface of the sun, those are magnetic storms.
Mm-hmm.
So we know that the sun has a magnetic field. It's a magnetic environment. If you want to understand the nitty-gritty detail of how the sun operates and all the phenomena we see, you can't exclude magnetism.
Right.
Well, one of the things that happens when you have a star that collapses that has a magnetic field is the magnetic field strength increases.
Mm-hmm.
And so we expect neutron stars when they first form then to be spinning rapidly and have very strong magnetic fields on their surfaces. And this allows them, because of the nature of the particles that are in the environment around the neutron stars, they have this beaming effect. The analogy here, what we use is a lighthouse to describe it,
Right.
where light can be beamed along the magnetic poles of the neutron star. Think of a magnetic north pole and a magnetic south pole.
And the reason this works is, remember, light, including radio waves, is electromagnetic radiation. So it's influenced by magnetic fields.
And we know that accelerated charged particles emit electromagnetic radiation, i.e. they emit light. And the light is emitted then along the magnetic poles such that it can escape the object, right? It gets emitted predominantly along the poles and get away from the neutron star. And just like the Earth, our geographic north and south pole is not lined up with our magnetic north and south pole.
Right.
If I gave you a compass and you're not using a GPS system, if I gave you a compass and go find North Pole, Robert, off you go.
I'll
Right.
end up somewhere in Greenland.
Well, you're not going to end up at the North Pole, the geographic North Pole, because they're not lined up
I'm not
presently.
going to wind up at the spin pole.
Right. And so in general, as far as we can tell, the magnetic poles don't line up with the rotation poles, the geographic poles of the neutron stars. And as the neutron star rotates, then you have these poles that sweep around like a lighthouse. And this beam of electromagnetic radiation, this light gets swept out and goes around and around and around. And the alignment is right. Then that beam passes by the vicinity of the Earth. It sweeps over the Earth, and we can detect that flash of light. Then because of the rotation of the neutron star, that beam is somewhere else for a period of time, and then it flashes by our location again, and we see a flash of electromagnetic radiation coming from the neutron star.
Right.
But these neutron stars rotate so rapidly, I mean, they're essentially millisecond pulsars, as we call them.
Yeah, it's
right?
millisecond times for each rotation.
Yeah, so they go around once in like,
Actually, some of them are microseconds.
Yeah, they go around once in like a thousandth of a second or so, right?
Right.
And so why? Because they are so compressed and so dense, even though they rotate rapidly, they don't break up because of the rapid rotation. They're able to rotate rapidly, more so than an object like the Earth, for example.
Right.
And so the time between flashes can be very short, like thousandths of a second. The most famous one, if you know anything about astronomy, is arguably the neutron star, or as we view the flashes, we call that a pulsar. They are just neutron stars that we can detect the pulses of radiation. There's one right at the heart of the Crab Nebula.
Yep.
And that's because it was produced by a supernova in 1054 AD that was actually observed from the Earth. People noticed the appearance of a new star in the sky and tracked it over a period of weeks and months to how it dimmed and no longer could see it. And they didn't have telescopes back in 1054 AD, but it was bright enough to see with the unaided eye.
Right.
And this is in the constellation Taurus the Bull. And when you point your telescope to that location today, you see this cloud of debris. It's a supernova remnant, the leftover debris from that exploding star that's expanding outwards. And at the heart of the nebula
is the pulsar.
Is a neutron star, a pulsar.
Yep. And I will point out, for those of you interested in such things, it is one of the first targets, right up there with the Ring Nebula and the Orion Nebula. The Crab Nebula is one of the first targets you learn how to shoot.
Yeah.
Because it is easy to target, it is easy to find, and you don't have to have hour-long exposures to get a good signal from it.
And the interesting thing about the Crab pulsar is it spins around once in 1/30th of a second. In other words, it spins around so fast, it goes around 30 times in 1 second.
Nice.
And so if you have something that flashes on and off 1/30th of a second, that's right at the limit of the eye's ability to detect. Now, you remember the old monitors,
right.
the CRT computer monitors, you see the little flickering?
Yeah.
And you could see it a lot of times out of the side or corner of your eye. And that bothered a lot of people.
Yep.
That's because the refresh rate was sort of at those frequencies that you can just barely detect with the eye.
Right.
The interesting story about the Crab Nebula is when pulsars were first detected in 1960, around 1967, I'm not mistaken. Eventually, one was detected at the heart of the Crab Nebula. That's the pulsar, the Crab Nebula pulsar. And we knew directly the connection, therefore, with supernovae, these exploding massive stars. There was an anecdote of a person. I don't know if I've told you this story. Back in the 1950s, the McDonald Observatory in Texas had public viewing. I believe it was on a Saturday evening, every so often, right? Whether it's every Saturday or once a month or whatever. And it was at a time when the public could come in and look through the telescope. I think it's 100 inch or 200 inch. It'll be 100 inch.
100 inch.
It's the size. Can't be
200.
200.
Is
That's Palomar. So 100 inch class telescope. So about 2 meter class telescope, as we would say today. And they would have people looking through the eyepiece. And the story is that a person was looking through the eyepiece, and she told the professional astronomer who was standing off to the side, the object is flashing. Now, the telescope at the time was pointed to the Crab Nebula. So this is before we knew about pulsars. They weren't discovered till over 10 years later.
Right.
Now, this particular person then mentioned that the object was flashing, and that I guess the professional astronomer, if the story is correct, started going on about twinkling, scintillation of the light, the twinkling of stars that you see due to the light coming through our atmosphere at different angles slightly, and you get this twinkling effect. If there was no atmosphere, the stars don't twinkle.
Right.
Okay? And then the woman who was looking through the eyepiece says, no, like I am a professional pilot, a commercial pilot that flies mainly at night, hauling cargo to point A to point B or whatever. I know twinkling. I have lots of time to look at the stars when I'm flying, right? I know what twinkling is. This is something else. This is not twinkling. And what happened was, I guess, the professional astronomer kind of just dismissed it or didn't think any more about it. But what she actually had detected because of her acute eyesight was the flashing of the pulsar in the heart of the Crab Nebula that wasn't detected again until over a decade later.
Right. And this gets into how our visual acuity is different for each person, because the actual average flicker rate, the recharge rate on your eye, is about 1/26th of a second. So 26 times a second. So it pulsing at 30 is beyond the limit of most of the half the people. But this lady was apparently one who had a little higher flicker rate.
Well, I mean, anytime you come up with a measurement, let's say the sensitivity of your eyes to certain light, there's not everybody's precisely going to have that sensitivity.
Right.
There's always, in statistics, what we call usually be a Gaussian distribution, a
Right.
bell curve, a spread in the ability of people. Some people wouldn't have as good ability as you. Some people would have better. So you have a range in capabilities. And this particular person had that acute ability to see that flickering at 1/30th of a second.
That's it.
So it's so in science, a lot of times discoveries and are serendipitous type of things. So if this professional astronomer would have followed up more, would have got an optical detector that was capable of detecting these rapid flashes, they would have detected these flashes coming from the heart of the Crab Nebula and would have discovered pulsars.
And the sad thing is such equipment existed at the time.
Yes.
Because all it would have taken was feeding it to a photodiode, a photomultiplier, and then feeding that signal to an oscilloscope, and you would have seen
Yeah.
the signal.
What you have to do, remember in science, take the trouble to investigate things.
Right.
Something that doesn't seem right, look at it in detail. Try to figure out why it doesn't seem right.
There you go.
You never know where that path leads you.
That's also why it takes imagination, folks.
Well,
You
that's
know?
why they say a lot of times when people get Nobel Prize, they are lucky in some sense because things just clicked at that time when they were doing their investigation or research, and they got lucky in some sense and followed certain things that otherwise
Right.
people dismissed or didn't notice.
There you go. So
Okay.
I'm going to pull us back into
Yes.
the target, and let's look at this picture.
So
finally,
with the discovery of the first pulsar, then with radio telescopes and doing wide area surveys, we discovered lots of these pulsars. So today we know of literally over 2,000 pulsars exist. You know, mainly I think most of them are in our Milky Way,
right?
as far as I
I
know.
think we have some in like Andromeda,
And they're
other
very
nearby
close galaxies, but
Right.
yeah, it's mainly in the Milky Way galaxy. And so people have been watching these pulsars, monitoring their flashing of their radio waves in this sense, because we're using a radio telescope in this case. And what we can do is precisely time them. They're extremely precise. That is, the time between flashes is even as good as the atomic clocks that we have here on Earth,
Right.
because of just the nature of the fact that it's the rotation. Now, energy is being used up as these pulsars emit light. And where does this energy comes from? Well, what happens over time is the pulsation then rotation slows down. So they rotate, the periods become longer and longer and longer. They spin down, as we'd say. And the strength of the magnetic fields get weaker and weaker and weaker. So that's ultimately where the energy is coming from, extracted from the rotation and from the magnetic fields.
field. Right.
But we can track all of that precisely with our atomic clocks and our radio telescopes. And so what happens, getting back to gravitational waves, is what we can do then is look at a system of pulsars spread over different regions of space around us. And we can watch the timing and looking at the timing of the emission. And the idea here, as you see on the slide, as a gravitational wave passes by us, right? In fact, it can pass by in the space between us and the pulsars. Gravitational waves, what they do is they stretch ever so slightly space and compress it in the other dimension, like the perpendicular direction.
Right.
So let's say if you think of X and Y, or think of the X-axis, I should say, and the Z-axis, right? It would stretch, let's say, along the X-axis and then squeeze along the Z-axis.
Right.
And that's what this is illustrating here with the sort of white oval, dash oval, and the blue dash oval. You have a pulling out and then a squeezing of space and then pulling out in the other direction. And so as this gravitational wave passes by, the distance between us and let's say a particular pulsar or pulsars, depending on where they're located, that distance will change. It can be stretched out to be longer, so it would take more time for the radio pulses coming from the pulsars to arrive on Earth, and we would notice that in our timing.
Yep.
Or it can be squeezed so that the distance between us and the pulsar or pulsars is shorter, and the signals will arrive sooner because they have less distance to cover.
And part of me goes, and they'd also be blue shifted or red shifted depending on which direction they were.
Yeah,
squeezed.
and we can track all of that. So
Right.
without a gravitational wave, you can measure all of that shifting back and forth, right? But remember, it's a rotation,
right?
right? And everything is orbiting around the center of the Milky Way. So it's not like if you just concentrate on the Milky Way pulsar, essentially all there are, you don't have to worry about the cosmological redshift. You have to look at the orbital Doppler
redshift.
shifting,
Yep.
right? And if some of them are approaching us in their orbit, right, relatively speaking, some are moving away, relatively speaking, but we can measure all that. This is an additional effect on
Right.
top of everything.
I was saying this is to be an additional part
effect.
of the blue or red shift. You know?
That's
Yeah.
right. So what has been done then, and so if you want to go to the next slide, Robert,
Oh, sure.
is that in the end of June, then it was announced for the first time a signal, a measurement of the stretching and squeezing of space due to gravitational waves by monitoring the signals coming from these pulsars. Now, these pulsars that we're looking at, there were about 68 pulsars. One of them wasn't great, so I think the final sample that you see on the plot here contains measurements from 67 pulsars. But what you're looking for is as the gravitational wave passes through space, passes through our region of the Milky Way, they will change that distance longer and shorter of the different pulsars depending on how close they are and where they are located in space. And the signal change, that is without the gravitational wave, the signal change is correlated, as we say, from one pulsar to another. So imagine a disturbance passing through, let's say between you and some source you're looking at in light. So I hate to use this analogy, but when you look at exploding bombs on the ground, you see this density shock wave propagate outwards. And how do you see that shock wave? It causes optical changes in the background that you can notice. And you'll
Right.
see that move away from the center of the explosion. Well, this is kind of what you're seeing here. You're seeing changes in the distance to these pulsars as the gravitational wave passes our region of the Milky Way. And so these signals from our sample of pulsars should be correlated. So
Right.
the plot you see here on the slide on the left shows this correlation. If there's no gravitational wave, then these data points, which are in red with the error bars, should all lie along that dashed horizontal line at the 0 mark. Notice the y-axis, the vertical axis, is correlation between pulsars. That would be 0 if there is no gravitational wave. But if there is a gravitational wave, and I don't mean one wave, there's going to be waves from all kinds of things happening, in our galaxy and beyond. As the space then changes, gets stretched and squeezed, the signals from these pulsars should be correlated. In fact, people have done modeling of this correlation that you would expect. The modeling is the dark solid line that you see passing through the data points. So the
Right.
data points, the red ones are observations. The black curve is the model of what you predict you should see observed if there are gravitational waves.
Yep.
So this was the announcement then that was done on June the 28th, was that, now notice there are large uncertainties here, but it looks very promising.
Right.
It looks like we've discovered this gravitational wave background that's permeating through all of space, including in the region that we exist in the Milky Way galaxy.
And I was going to point out a couple of things. Like, one, as we get better at detecting these things and using this method, those error bars are going to shrink. They'll get smaller. So that's one thing to look out for. And another thing, because I'm bringing these points up because a lot of people ask, how do they know that? Okay, this gets into how we know that. And the other part of that is in that little lower text box, lower right one, NANOGrav 15-year measurements. This data was collected over 15 years. So they made sure they checked it and checked it and checked it and checked it against new measurements for a long time before they said, look what we found.
Yeah, and they even announced a few years ago that it looks like there's some signal here, some correlation that's not
Right.
0, but the data wasn't robust enough. So they had to wait until the 15-year data and just like, yeah, there's something here. let's publish it, because there are other experiments. This is not the only, NANOGrav is not the only experiment out there. There are other ones that are trying this as well. So there's always a competition in science.
There's always a rush to be the
Yeah,
first.
you want to publish first, right? If you're, you got to be the first one to publish the result before anyone else to get the full credit for it. But
Right.
you don't want to publish too early, and it turns out that this signal is wrong. And there's been famous cases in the past where people have rushed to publication or make press announcements, and they turn out they had to retract later on, embarrassingly.
Oops,
and so you don't
we
want to
were
get
wrong.
caught in that. Go look up the bicep type of measurements that were
yeah.
done a few years ago as
Was
an
that
example.
the one with the
Polarization
of the background?
Yeah.
Yeah.
The CMB polarization. Anyways, also notice that there is another sort of oval up to the right side. That's an all-sky projection showing the location of the pulsars that were used in this 15-year data set. And the blue symbols around are the ones that were taken by Arecibo's, they're blue circles. The solid green circles are the one that was taken by the Green Bank telescope, which is the one that I showed you. And this sort of, I don't know what you call that shape, but is the ones taken by the VLA, that funny propeller-looking like symbol that they have there.
Well, that's because that's the shape of the array.
Yeah, it's the shape of the
VLA
array.
is the
That's
very
a
large array.
Y-shaped symbol.
Yeah.
That's what it is.
It's the very large array, by the way.
Exactly. And so that data set is over 15 years. So allowing enough time, of course, the signal will get better and better and better. But
Yep.
we detected now gravitational waves for the first time. And so if you accept this detection, the next question you should immediately think about is, what is the source of these gravitational waves? So there was a lot of nitty-gritty analysis that was done in this study, and there are a lot of papers, a series of papers that have been published, or at least been submitted for publication, and they're in the review process. I don't know exactly where each paper is in that process of being published, but in those analyses, there are different types of analysis. If you're into analysis, or Bayesian type analysis, the frequency type analysis, they used all the tools that we have at our disposal from statistics to look at this and look at these analyses, trying to figure out what is, many things, but one of the things, what is the source of these gravitational waves? Now, what we think of is from the merging of binary supermassive black holes. That's the best guess based on the data. It's not a guess, but based on the analysis,
Right.
this is what we think it is.
It's better than a guess.
Yes, it's better than a guess, or a best estimate, I guess would be the proper way of saying that. Now, there's some talk that it may be signifying something from the very early universe. That's related to something that we've talked about in a previous podcast, also known as the Hubble tension. I won't get into what it is because for the lack of time here, but it's the fact that the expansion of the universe, what we call the Hubble-Lemaitre constant or the Hubble constant today, differs depending on the different way you measure it. So you get a lower value if you use the cosmic microwave background measured from the Planck satellite. You get a higher value if you use supernovae and Cepheid variable stars and so on. And there's like a 5 sigma roughly discrepancy, and that's enough in science to say, hey, there may be a real difference here. What causes that? That's
Right.
known as the Hubble tension. And so and to get around how you solve that, one way is to assume that there's some kind of form of dark energy, which we've also talked about at length in previous podcasts, that is not the same as the constant dark energy, the cosmological constant that we think best describes our universe presently, that there's a different form of this dark energy that results in this Hubble tension. And that could also add to this signal gravitational waves. That's
Right.
the tie-in here.
Okay.
But the most likely, right now, the most likely source are these merging supermassive black holes. Now, the thing to note is the NANOGrav instrument detects very long wavelength gravitational waves. We're talking about light years, multiple light years, many light years in length, where the gravitational waves that are detected by LIGO are very, very, very
small.
short, very
Yeah.
short wavelengths, very high frequency. So they're detecting different types of frequencies of gravitational waves, very low frequency for this detector.
Right.
And the motion, if you think of it, the combined motion, imagine you have multiple supermassive black holes that are merging every now and again, and all of that signal is passing through because they're at different distances and takes time. They can travel no faster than the speed of light to reach us. So that those signals are passing through. And so it's almost like you had a buoy in the middle of the ocean. And this buoy is bobbing up and down, not due to waves caused by one passing boat, But imagine that there's lots of boats in the vicinity, and it's the combination, the superposition, if you like, of
Yep.
all of those water waves that's causing the buoy to have its up and down motion.
Well,
And that's what we're detecting here.
right.
But of course, it's gravitational waves.
And it's funny you mention that because I noticed in an airplane coming in over the Atlantic one time that, we were still 3,000 feet in the air, but I could see the waves. Well, I knew off the top of my head there was no way I could see individual waves. Their amplitude simply isn't large enough to see from 2,000, 3,000 feet in the air. So what was I seeing? I was seeing the long wave superposition, the longer wave wavelength that was coming through. So that's another way of thinking of it, is sometimes these waves travel at different speeds and they have another wavelength on top of them because of that.
Right. So the source that they think now is the best estimate of these gravitational waves are these merging supermassive black holes. But do we have evidence of this occurring? Well, it was interesting when I read this. It's like, wait a minute, I was involved in a study that was done a few years ago that's related to the merging of supermassive black holes. So this was a paper that collaborators Paul Green at the Smithsonian Astrophysical Observatory, it's within the Harvard-Smithsonian Center for Astrophysics, Adam Mayers, who's at, I believe, the University of Wyoming now, if I'm not mistaken. He was a postdoc at the time that this study was done, and myself. And so, and there's others as well included, but just to focus on the study, for the lack of time here, is that Adam had this idea of looking through sky survey. This was the Sloan Digital Sky Survey,
Okay.
of looking for quasars. So the heart of quasars, these are known as active galactic nuclei. They produce a tremendous amount of light. They're very, very luminous, and mostly they're very, very far away, billions of light years away on average. But these quasars, the heart of these quasars are supermassive black hole with an accretion disk. So the material in the accretion disk is spiraling in towards the black hole, and as that material gets heated up through frictional forces and so on, it emits electromagnetic radiation, of course. And once that gas passes the event horizon, it can't get out of the black hole, so you don't see it. So you're seeing the light coming from quasars, but it's the light coming from the accretion disk outside of the event horizon of these supermassive black holes. And what Adam was looking for was quasars that were close together in space and also at roughly the same distance from us, what we'd say the same redshift. And so he called through the catalog looking for these candidates. And what Adam and myself had done is we went to the 4-meter telescope at the Kitt Peak National Observatory to image these candidates in optical light to see what we could see. And when we came across this source, which has the very fancy name, SDSS, that just stands for Sloan Digital Sky Survey, and then it's the coordinates. J1254, that's the right ascension. 0846 is the declination. So it gives you right away where, if you know right ascension declination, the sky coordinates, as an astronomer, you know roughly exactly where that object is, roughly where it is. And so when we took an image of this particular candidate, we've seen these tidal tails. So the quasars are observed in X-rays. That's the white blue light that you see there. And then the tidal tails you see outside of that is an optical image taken with actually the 6.5-meter telescope in Chile. The Walter Baade telescope is one of the Magellan twin telescopes. So when we took it with the 4-meter telescope, we seen tidal tails. And that's a sure sign that these quasars are at the center of two galaxies. They're each in their own galaxy, and they're clearly interacting with each other, sort of merging together, if you like, creating these tidal tails, these S-shaped tails that you see here. And once we realized this, we got a hold of Paul Green, who's part of the project also, and first author on the paper. He got a hold of John Macaulay at the Carnegie Institute. He was at the telescope down in Chile when he got a hold of him, and he said, I'll take an image of it for you. And he took an image, and that's the image that you see. Now, the Magellan telescope was operating under much better sky conditions than we were in Arizona, and also it is a 6.5-meter telescope versus the 4-meter telescope we were using at Kitt Peak, and therefore you got a much higher quality image. And that's the image that you see here combined with the X-ray image. So this was smoking gun evidence for the interaction of two quasars, two galaxies that are interacting. And why this ties into what we talked about with NANOGrav is that ultimately what we expect to happen is that these two supermassive black holes that are responsible for these two quasars will merge together. And when that happens, they will create a burst of gravitational waves that
should be high amplitude, long wavelength.
which would be detectable by hopefully by our gravitational wave telescope. Now, this source is really far away. It's 4.5 billion light years away, and the separation at the time we took these observations is not going to change any really now. They're about 70,000 light years from each other, the center of the two quasars.
Right.
Given the distance and the angular separation between the two, you can come up with a physical length. So these will ultimately merge together, as far as we know, creating these bursts of gravitational waves. Now, of course, this will take a while for this to happen. We won't be around, but in the distant
speak
future,
for yourself.
Yeah, in the distant future, this may be detectable. But these are the kind of objects that ultimately are producing, as far as we know, this background of gravitational waves that were detected from this NANOGrav experiment.
Nice. Very nice.
Now, there has been other news lately. I don't know how much we get. We can save some of this for the next podcast, Robert, if you like. But let's go on to something we promised to talk about today, and that is neutrinos.
Okay.
So if we go to the next slide, the announcement that was made also, I believe, was near the end of June, was the detection of neutrinos coming from the Milky Way. And this is with the experiment known as IceCube. So what is IceCube? Well, IceCube is an experiment where people went to the Antarctic, drilled down into the ice with high pressure hot water to plow their way down through, and look at the lengths here, up to almost 3 kilometers in length. Imagine that, almost 3,000 meters down. And what they lowered down in that hole before it has a chance to, get through the ice, of course, right? And then you're down into the salt water, is that you lower down these strings containing these optical detectors, like photomultiplier tubes.
Right.
And so they lower them down on these strings. And notice that there are a lot of these strings hanging down. There's over 5,000, as you look on the slide here, that are deployed. And what happens is neutrinos that are released from a lot of sources, including nuclear fusion. So lots of neutrinos are coming from our sun. Nuclear fission, there's lots of neutrinos coming from our nuclear power plants here on the Earth.
Right.
Right? In fact, if I'm not mistaken, neutrinos were first discovered, or observed, I should say, by having detectors set out just outside a nuclear reactor here on the Earth.
Oh, wow.
Because that's the flux of neutrinos is very high and increases the probability of detecting them. Now, not that long ago, before the mid-90s, we thought neutrinos had no mass at all. So they would travel exactly the speed of light. But we realize they have a little tiny bit of mass. So they travel a little less than the speed of light. Very close, but a little less. But they interact through what we call the weak force with matter. So neutrinos on average can, the analogy is they can pass through light years of a lead block, if one existed, without even a single collision. But if you have enough of them and you wait long enough and you have a dense enough material you're looking at, eventually you'll have some collisions.
Right.
So it will occur.
Right? Right. It's a matter of statistics.
It's a matter of statistics. So what this experiment measures is that when neutrinos go through the Earth, and that's essentially what they're measuring, from the north and come down through all of the Earth and then interact with the ice in Antarctica, occasionally collisions will occur. And what they'll do as they travel through this ice, they are traveling faster than the speed of light in the vacuum through the ice. That's faster than the speed of light in the ice itself. So they travel less than the speed of light in the vacuum, but faster than the speed of light through that material body, the ice itself.
And that is not a contradiction.
No.
But it would take a whole podcast or more to explain.
Just think of it this
how that
way.
can happen.
Special relativity tells us that essentially locally, that two objects can't travel faster than the speed of light in a vacuum. They leave that off a lot of times. But these neutrinos can travel through the ice faster than the local speed limit of light through that ice. And when they do so, they emit what's called Cherenkov radiation. And these are light, you can think of light being emitted from these neutrinos. And that light can be detected by these light detecting devices that they have lowered in the ice in Antarctica. This experiment has been running for a while. If you want to look at the results were announced, and the results show us that there is neutrinos that they observed coming from the Milky Way. So the top panel shows what the Milky Way looks like in optical. The center of the Milky Way is the center of the top panel. The next panel down, the second one, is what we observe in gamma rays, mainly to be Fermi observation. The third panel is the prediction of neutrinos, given the sources that we know exist in our Milky Way. And then the fourth panel then is the actual detections. The fifth panel, the bottom panel, just looks at what is the most significant detections. You think of it that way. So we know they are detected for the first time using this instrument, IceCube, then this background of neutrinos coming from our own Milky Way. And not unexpectedly, most of these high energy sources that are creating neutrinos in our galaxy are near the central region of our Milky Way. And that's where you see the greatest significance of the detections, is near the central region of the Milky Way. It can't detect at this moment individual sources of neutrino, but sort of a broad general region of where the higher density of these sources, where these neutrinos are coming from. Right. And so it's a wonderful thing, you know, showing us the progress of these type of detections. Okay, so I think this is a good time. We've kind of run out of time. We'll continue this discussion with other things that have come in the news lately in the last couple of weeks. We'll look at that next day. Our next podcast, by the way, is on Tuesday, July the 18th, okay, at 3 p.m. Central Daylight Time. If you're interested in science, if you like what we talked about, please give us a thumbs up. Please subscribe if you haven't already. And by the way, to give a thumbs up, you need to then sign in to YouTube.
Right.
If you don't sign in to YouTube, you're not allowed to hit that thumbs up button and make it count. So
right. Basically, they want to know that it's an actual account, not just us spamming the like.
Exactly. And so please do that if you're able to. If you're interested in science at all, please come to the University of North Dakota. We have a fancy slide, as you can see.
Yeah, our nice department was willing to put this together for us. So, or the College of Arts and Sciences. So, anyway, there's lots of online degrees, so you don't even have to come to North Dakota. We've got programs for you. So we'd like to see you here, but at the same time, you don't have to come to North Dakota to attend classes here.
No, if you come here and you want to talk to Rob and I, we'll guarantee that if you email us personally, we will Zoom with you.
Absolutely.
And so you'll get a personal conversation of Robert and I with you directly. How's that for a pivot there to get them to come?
Email me, we'll talk with you. So.
Now, if you want that, so we always leave you with a quote at the end of the podcast. So let's go ahead and do that for the sake of time now. So this quote is actually from a Nobel Prize laureate.
All right.
We've talked about the inside of atoms. We talked about protons and neutrons and these sort of things. So the name of the scientist is Frank Wilczek. So he got the Nobel Prize in physics that related to the quark model that described what happens inside of protons and neutrons. And his quote is, "If you don't make mistakes, you're not working on hard enough problems." And that's a big mistake.
Ooh, I like that one.
So thank you very much for watching, and we'll see you next time.
See you next time, folks.